Hello everyone. In this video I want to tell you about the method of sun sensing for planetary rovers. Sun sensor is a navigational instrument used usually by spacecrafts. So why do we need sun sensing? Usually, rovers use their internal measurements such as visual odometry, wheel tachometer and internal navigation sensor for their navigation, which provides significant error over time and distance. So, we would need some external reference to minimize it. We have a few possibilities provided on Earth, such as different global navigation systems, magnetic compass, and more of a hobby or history project for us in everyday life as of the practical use navigation with sun and the stars. But this is on Earth. If we are talking about other celestial bodies, then we don't have any GNSS, and in quite a few cases, like Moon or Mars, the magnetic field don't exist either. That's how we are quickly left with one of the oldest navigation techniques. And in this video, we are talking about the navigation using the sun. Of course, there is a reason why in everyday life other methods are preferable. This method has some problems that are difficult or just impossible to avoid. Sun changes its position. Firstly, of course, through the day. Then, position depends on the day of the year, and the last but not least, the pattern will be slightly different for the different locations. The other big factor is the weather. We can't navigate with the sun when we can't clearly see the sun. The dust coverage would cause a light diffusion, not to mention that it is very bad if the dust remains on the sensor. Clouds are also making the precise search for the sun much more difficult. Good news here. Weather is only a factor when a celestial body has an atmosphere. There are two main principles that sensor can use. First is more based on our understanding of navigation with the sun. We see the sun and then we calculate our position and our heading. Those sensors are using camera and then process the picture. The second method is more inspired by nature. There are certain insects that are using light polarization to navigate, for example, the ants in Sahara Desert. For visual concept, I will use the Meapan cam as an example. So firstly, we need to find the camera, optics and controlling. Here was used the CCD, charge coupled device. Then, because it is quite sensitive and we literally want to look at the sun, the neutral destiny filter is needed. Here is ND25 is chosen and it's allowing only 25% of the light to go through. The color filters are there to make the extraction of the image easier. Then, when the hardware is chosen, we can calculate how long the exposure should be, because the output image would be influenced through some factors such as what is the power density on Mars, how much of that light would enter the camera, how much would go through the whole optics and end up on the sensor, how much of what's already left the sensor would detect. When we have the image, the next step is to find the sun centroid. This is one possible algorithm to do it. First, we would calculate the dark current row average of the picture. Subtracting it from the image would remove fixed beta noise. The angular size of the Sun on Mars would be 0.35 degree, which would be seen by the sensor as a circle approximately 22 pixels in diameter. Then, by moving square window with a side of 29 pixels, so a little bigger than the pixel image of the Sun, we can calculate the brightness of the pixels inside and search the brightest one. This would mean that the Sun is now in this frame. Then, based on the brightness of every pixel, the centroid of the Sun can be calculated. This calculation would be done twice, and after the first time, frame would be moved to the calculated values before performing calculation the second time. This would eliminate the error caused by position of the window and search for the brightest window in the picture. When we have the Sun centroid, with a simple pinhole model, we can calculate the 3D vector from our sensor to the Sun. We can use this model because size of the Sun in the picture is small enough for simple transformation and can be seen as a point. With basic frame transformation, we can move the vector to any other coordinate system, for example, to the rover body frame. This transformation would only depend on the structure, or we can move it to the frame outside of the rover. As I earlier said, this method is more inspired by nature and uses a polarized vision. Polarization in the sky occurs because the sunlight is scattered by the atmospheric molecules. Direction and degree of polarization are built on the mirror symmetry pattern that stays this way while rotating around zenith. The property that along the symmetry line the E vectors are always perpendicular to the solar meridian is also independent of the rotation. For the detection of polarization, the polarization opponent unit is used. Color filter at the top represents the blue sensitivity of the receptors of the crickets. Then, each unit contains two identical polarized light sensors with linear polarization axes that are perpendicular to one another. This would mimic the crossed analyzed configuration of the insect eyes. Normalizing and subtracting the both outputs in log amplifier would provide the clear output as a function. And then we would have this unit 3 times and so installed on the rover that the polarization axes of the positive channels are 0, 60, and 120 degrees to the robot body axis. The crickets have the similar structure in their eyes with approximately 10, 60, and 130 degrees to the body axis. The two methods can be used to extract the compass information. First is by regularly performing the scanning of the sky by rotating around the vertical axis. Rover would find the solar meridian and use it for the reference direction in the later movement. The second is by continuously scanning and comparing the output with a lookup table. This table would be created at the beginning of the experiment by rotating once around the vertical axis. Due to cross-analyzer configuration, neither of the methods is dependent on light intensity. What left to eliminate is dependence on the degree of polarization, which changes through the day. For scanning model, it can be done by evaluating only the maximal signals, because we are just searching for the solar meridian. For simultaneous model, It can be done either by regularly updating the lookup table or by normalizing the outputs. In conclusion, the sun sensing can improve the rover navigation system. It is still questionable in certain conditions and would provide the best results in cooperation with the rover's internal navigation sensor. Here are the examples of some not so good weather condition images. On the left, it is also difficult, when not impossible, for the human to say where the sun should be, but it's still mostly because of the image quality. Still, the algorithm was able to provide a sun vector with over 75% confidence. And the image on the right is a post-procession version of the other sun picture. It is also provides an example that we can firstly eliminate every not circular object, and secondly, all objects that are too small. Here, based on this criteria, all not sun objects were eliminated. Also, polarization concept cannot be used on the celestial bodies without atmosphere, because then there would be no scattering of the light. And that concludes the video. I hope you enjoyed it.